Here we go. Today we're going to be talking about chemical reactions in everyday life. Well, at least a bit of it. We're going to be speaking more about the general kinds of reactions that we can get, what they look like, and the equations for them that you guys have to know. So jumping right in, our first reaction is burning. So this is what happens when we burn pretty much anything. It can be a liquid, it can be a gas, it can be a solid like wood. If we are burning something, we have some kind of fuel. We combine it with some oxygen and some heat, and that gives us carbon dioxide and water and some more heat. So this fuel is normally what is known as hydrocarbons. Okay, what this means is we've got some hydrogen molecules and some carbon molecules all stuck together in slightly bigger molecules in order to give us the fuel to burn. So this reaction you guys need to know, the fuel plus oxygen gives us carbon dioxide and water. Okay, so here's an example. Propane. So propane is the gas that you get in the cylinders that you can use for gas fires and things like that. That cylinders full of gas that you have for burning is normally propane. So this is its chemical formula, C3H8. You don't need to know the chemical formulas. I'm putting them here so that you can see what's happening, where these things come from. Okay, so we've got propane, we combine it with some oxygen, we get carbon dioxide and water. So here we've got some carbons, we've got some hydrogens, and here we've got some oxygens, and they combine into carbons, oxygens, hydrogens, and oxygens. Okay. So you'll notice that there is a 5 over here. So we have to combine it with 5 oxygen molecules in order to have a complete burning. So to have all of it turned into carbon dioxide. What happens if we don't have enough oxygen? So if we had this same reaction and we had less than 5, we would end up with some carbon monoxide or just some carbon and some water. So this is the reaction for an incomplete burning. That means that we don't have enough oxygen. So we have our fuel plus our oxygen, whatever bits of oxygen we have, gives us carbon monoxide, carbon, and water. This carbon is soot. That is the black powdery substance you find on the inside of chimneys. That's the reason why the chimney sweeps in Mary Poppins are completely covered in black stuff. That's where that comes from. Carbon monoxide is a gas. And it's a fairly poisonous gas for this reason. Carbon monoxide can be absorbed by your lungs, where it binds with the hemoglobin in your blood and your red blood cells, which prevents your red blood cells from being able to transport oxygen to the places in your body where it's needed. So you end up having to breathe more. It feels like you're out of breath, but in actuality, what's happening is the oxygen can't be transported to where it's needed in your body. The main way they would counteract something like carbon monoxide poisoning is with a blood transfusion or something along those lines. Or if it's not too bad, literally waiting it out and waiting until your body makes more red blood cells to replace those that have been poisoned. So this is not a great thing. So carbon monoxide tends to be made in places where we have a restricted airflow. So this is places like furnaces, kilns, things like that, where you are carefully regulating the airflow in order to get specific temperatures and things like that. We tend to make quite a bit of carbon monoxide in reactions like that. So in terms of things that you guys know, car engines quite often have a problem with making carbon monoxide. And that is why the computers and things that you have in your car is constantly regulating the fuel mixture that goes into the engine. The fuel mixture refers to the fuel mixed with some air from outside in order to have combustion take place inside the engine. So if there is not enough oxygen going into your engine, you end up making carbon monoxide. So in the exhaust pipes of all of the cars nowadays, there are specific filters and things that filter out carbon monoxide so that we don't end up putting lots of carbon monoxide into the atmosphere. The carbon that you would get, this is very often what happens if you have a car in front of you on the highway and it's a fairly beat up old car and it's just a big cloud of black smoke coming from behind. So that essentially is a lot of carbon that that car is making. So it doesn't have much oxygen at all. So you end up getting this big cloud of black carbon. That does not get scrubbed out with carbon monoxide filters in the exhaust system. So definitely not good for the car, because that carbon, that soot, ends up putting a lot of wear on the engine. So people want to avoid that, but sometimes your car breaks and you end up getting this. It happens. Try and fix it. Okay, so that is incomplete burning and burning. Okay, now we're moving on to respiration. This respiration I'm talking about here is not the physical breathing in and breathing out that you are doing. What I'm talking about here is cellular respiration. Cellular respiration is the process inside a cell where it takes some glucose in, it takes some oxygen in, it combines them, and then it releases carbon dioxide and water. And it does this so that it can get some energy. So we have glucose, we've got oxygen, and it gives off carbon dioxide, water, and energy. This energy is in the form of chemical energy that you can then use in order to make your muscles move, make your cells do the processes that it's supposed to do. So instead of us getting heat energy, we are now getting chemical energy from this. So that reaction should look fairly familiar. Here we had a fuel plus some oxygen gives us carbon dioxide and water. Here with cellular respiration, we have glucose plus oxygen gives us carbon dioxide and water. So it's actually pretty much similar. It's the same process. It just happens at a much smaller scale, molecule by molecule, and so it's very, very controlled. So this is essentially a burning reaction. So you guys don't need to know these bits. You don't need to know them. I'm putting them here so that you can see what happens. So glucose is a bunch of carbons, a bunch of hydrogens, and a bunch of oxygens. C6H12O6 combines with oxygen to give us carbon dioxide and water. So this bit is definitely not in your syllabus, but I get asked this question fairly often. So what happens when you lose weight? Does it just pass through your digestive system and out into the toilet? Are you sweating out all of that weight? What is happening? Here's what's happening. The fat that is stored in your body is called triglyceride, and it has this chemical equation: 55 carbons, 104 hydrogens, and 6 oxygens. So that is quite a bit bigger than our glucose over here. So it gets combined with 78 oxygen molecules to give us 55 carbon dioxide molecules and 52 water molecules. So what happens inside your body is if you don't get enough glucose into your bloodstream, your body will start trying to convert the fats in your body into energy. This is a slightly longer process than just using glucose, so it doesn't happen in this specific way. So what happens is the fat in your body goes into your bloodstream from the fat cells. It then goes through your liver. In your liver, it gets converted into various ketones. These ketones are a lot shorter, smaller molecules, sort of like the glucose from the one previously. And that the ketones is actually things that your cells can then use in order to go through cellular respiration. So you get slightly less energy out of ketosis, the losing weight using fats, than you would out of using glucose. So if you have excess glucose molecules in your system, they will combine them together in order to form triglyceride, the fat molecules that can then be stored in your fat cells for a very, very long time until it is needed. So it gets converted into ketones, which your cells can then use as fuel. So in terms of where your body mass goes, for every 10 kilograms of fat that you are burning up, you need to take in 29 kilograms of oxygen. So that is breath in, breath out, a lot of oxygen coming in. So 10 kilograms of fat combines with 29 kilograms of oxygen. That gives us 28 kilograms of carbon dioxide that we are breathing out and 11 kilograms of water. This water goes through our systems out into the toilet, or we sweat it out, or our bodies can actually use it, whatever happens. So that is where your weight goes. You don't have all of your fat converting into muscles. If you are doing a lot of exercise, what's happening is you're not taking in as much food, so you don't have as much glucose in your bloodstream. That means your body decides it's going to start using fat. So it's literally just going through that reaction up here to convert fat into energy. But then it uses that energy in order to build more muscles, because you're using your muscles more when you're exercising. So they say fat converts into muscles. It doesn't. Fat converts into carbon dioxide and water. You are just building some muscles from the energy that you get from that. So that's where your weight goes. So this bit about the fat is not in your syllabus. You need to know about respiration. You don't need to know about losing weight. So now we move on to other chemical reactions. Neutralisation reactions. So this is when an acid combines with an alkali. And what happens in that is we end up getting salt and water. So here we have an example. We have hydrochloric acid and sodium hydroxide, and it combines to give us sodium chloride and water. So here's our hydrochloric acid. Hydroic means we've got a chloride ion. So we have HCl over here. That H means we've got an acid. That combines with sodium hydroxide. So what happens is that sodium combines with that chlorine. So these two combine, and now these two will combine, that and that bit, in order to give us the water. So those combine, gives us the water. These two combine to give us the sodium chloride. You guys don't need to know the symbols. I'm using the symbols in order to show you guys what's happening. Normally, you guys will get a hydroxide as your salt. So like sodium hydroxide, any kinds of things like that. So that's what's happening in an acid and alkali reaction. So another question, what happens with vinegar and baking soda? You normally get bubbles when you make vinegar and baking soda. Where is the bubbles coming from? So the vinegar acid is called acetic acid. It's inside vinegar, we've got some acetic acid and some water mixed. So this is what acetic acid looks like. There's our H, and this over here is the acetate ion. Then we've got some sodium bicarbonate. So there's our sodium. These two are going to combine to give us sodium acetate as our product over here. But this bit over here, this H, is going to combine with this HCO3 over here. And because we've got some carbon in here, we're going to end up getting carbon dioxide and water. So it's going to give us two products over here, H2O, so water, and some carbon dioxide. And this bit is going to end up going there. So this specific reaction, you guys will not need to know. You guys need to know these kinds of reactions. An acid and an alkali gives you a salt and a water. But now you know where the carbon dioxide comes from when you mix vinegar and baking soda. So now we continue on to displacement reactions. So displacement reactions happens when you've got a salt, this is a chemical salt, not your normal table salt, dissolved in water. So this salt that we have here is a metal combined with a non-metal. So this will have a slight positive charge and this one will have a slight negative charge, and that is essentially a salt in terms of chemical terms. So we've got a salt dissolved in some water, and then we add some kind of metal to that. So here's an example. We have copper and silver sulfate. So what's going to happen is these two are going to swap positions. So in our results, we're going to have copper sulfate with some silver. So essentially what's happening here is the silver is giving its charge to the copper. The silver then ends up sticking to whatever metal thing there is. So we had some copper over here. The copper, some of it dissolves into the water, and in its place, some silver forms on the surface of the metal. This is one of the ways in which we get silver-plated objects. They would take, say, the spoon or something, they would coat it in a thin layer of copper, then they would put it in a silver sulfate solution. That thin layer of copper will dissolve out, and the silver will start sticking to the spoon, and you end up getting a silver-coated spoon, so a silver-plated spoon. The other way you can silver plate things is using electrolysis, which is another kind of reaction, which we won't be covering right now. So one of the ways we get silver-plated objects. I've got a video I'm going to show you guys about this in a bit. I just want to go through the work first, and then we can watch some videos. Oxidation, sorry. This is rust, corrosion, or tarnishing. Rust refers to iron, corrosion refers to other kinds of metals, tarnishing refers to things like silver or brass. Sorry, my voice is busy going, so give me a second. Okay, so what happens here is we have a metal that combines with some oxygen in order to give us a metal oxide. So here's our example. Iron plus oxygen gives us an iron oxide. This is our normal rust. Salt water acts as a catalyst for this kind of reaction, so things tend to rust faster if you are living by the sea. So I have a few pictures to show you guys. So this is some silver forks and spoons. This blackishness that you get here, that is the tarnishing happen on the silver. That is silver oxide forming on the surface of the spoon. So this is some copper pennies that was stuck in the ocean. And that bluish green color that you get over here, that is the copper oxide that is forming on top of the layer of the copper pennies. Okay. So I'm going to scroll down a bit. So here it's talking about the silver tarnishing and the copper. So silver tarnishes, it gets a thin black layer all over it, and copper corrodes and gets a greenish blue layer on it. So some fruits and vegetables that we get, for example, bananas, potatoes, apples, avos, all of these things, if you cut them open and you leave them out in the air, they tend to get a brown layer, or they go brown or black on their surface. And this is an oxidation reaction. If you want to prevent this kind of reaction taking place, you can either take a little bit of lemon juice and put it over your bananas or potatoes or apples or whatever you're using, and that will coat it in a thin layer, and that will prevent your actual apple or something from touching the air and forming this oxidation reaction. Another thing that you can do, say you're making mashed potatoes and you're chopping up all of your potatoes and you don't want them to go brown, you just put them in a bowl, pour some water over it, and then leave them soaking in the water. That water will prevent it from touching the air and forming this oxidation reaction. So your potatoes won't then go brown. So continuing on to metals reacting with water. This is specifically group 1 on the periodic table, is the alkali metals. So if alkali metals reacts with water, you get a metal hydroxide and hydrogen gas, and quite a bit of heat. So sodium and potassium can react very violently. It can even explode when reacting with water. And calcium and magnesium react a lot more slowly. So you would get some bubbles forming from this reaction instead of big explosions. So let me show you guys that quickly.
If we continue down the column for potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium.
Okay. Now I want to show you guys what happens when you mix quite a bit of potassium with water. Here we go.
Yeah.
Ready?
Yeah. Very.
Okay. So that's what happens when you add quite a bit of potassium to water. It is not a fun thing. So, yeah, I will post the links, don't worry. And I will speak about that in a second. Let me just finish this quickly. So our last few kinds of reactions, we've got metals reacting with acids. So if we have a metal reacting with an acid, we get a salt and some hydrogen gas. So here's our example. We have magnesium combining with hydrochloric acid. So the hydrochloric, that hydroic tells you that you've got a chloride over here. So you're going to get magnesium chloride and hydrogen as your products. So this is a metal reacting with an acid. Okay, and that is it for this. So now I just want to show you guys the last video that I have, which is about displacement reactions. So he's going to show you copper sulfate and iron reacting. So you've got an iron nail, and you've got a copper sulfate solution. Now he's going to add the iron nail into the copper sulfate, leave it for 10 minutes, and then he's going to take it out. He's pouring off the copper sulfate now. And now if you look at the iron nail, we have a layer forming over the top of it, and that is our copper layer. Now he's going to show copper and silver nitrate. So he adds the silver nitrate into the flask. He's got some copper wire in there already. So 10 minutes later, this is what we get. So this is what we get. We get quite a bit of buildup on the sides of our copper wire over here. Okay.